That's a no. No sleep for you until the end of the term.
I had a friend over, so no.
Yes, but that counts as sleep because your brain was resting.
That is, well, kind
Wait,
of.
what did you have?
I had a friend over.
Nice.
So,
Pretty, pretty.
who didn't get sleep and started on the PSET instead?
I mean, I started on the PSET.
You didn't start on the PSET, you had a friend over, come
No,
on.
I started on the PSET yesterday.
Okay, cool. Sorry? Printing it out? Yes, that's what I do too, so that I can say I started on it.
She left on Monday, so I had Tuesday.
Okay, cool. Who looked at the code? Okay, only 2 people started, but everyone else looked at the code. I like that. That's good, that's good. So, so the things we can talk about today. We can talk about this code. We can talk a little bit more about hash functions. And we can talk a little bit more about amortization. What do you guys want to hear? Okay, so 1 vote for amortization. So who wants to look at the PSET code? Who wants to talk about hashes? Who wants to talk about amortization? 2, 3, 4, 5. Okay, so then let's try this. Let's look at the PSET code and talk about amortization a bit at the end. I do have to talk a little bit about hashes, though, because I owe someone a question from last time. And the question was, we have rolling hashes. So the hashes look like this. Key, where key is a big number, modulo p. And we argued that it's really nice if p is a prime. And then the question was, what if instead p is 2 to the w and is not prime, as long as the base that we're using is coprime with p? Does this work? And the answer is, I didn't want to say yes without making sure that I don't say something stupid, but the answer is yes, this works just fine. Because the way you compute multiplicative inverses is you use something called the extended Euclid's method. And if we have B and P, then if we compute their GCD, that's like greatest common divisor. So GCD greatest if you use extended Euclid, you get something like xb plus yp equals GCD of B and P. So if this is 1, then you have xb plus yp equals 1. And if you're working modulo p, whatever that is, then you have that xb is 1 mod p. So there's your multiplicative inverse for. Well, so now that's nice math, right? But that doesn't tell me why are we not using this. So the multiplicative inverse would work. But there's something else that's wrong with using 2 to the w. Will this give me a good hash function? OK, the fact that it's p might be confusing. So let's say h equals key mod 2 to the w. And remember that the key is some digits in base b, right? It's a big number made out of digits in base b. So k is d1, d2, d3, all the way up until d length in base b. And I'll make things easier and say that b is 2 to the 8 because we're working with ASCII characters or colors or something that fits nicely in a bit. So what could go wrong with using this?
If your k is bigger than 2, if its k is bigger than 2 to the w.
It will be, for sure.
Yeah, so that's a problem, because then you'll loop. You'll get the same hashes for.
Yeah.
Right?
Yeah, so you will get, so hashing takes a lot of possible inputs. and maps them to a relatively small set of outputs. Input, hash, output. And we argued last time that we're going to have collisions no matter what, because we have a ton of inputs and not that many outputs. For example, if we're hashing strings that are 1,000,000 characters, then this is going to be 2 to the 8 to the 1,000,000 possible strings. And then the number of possible values is, if we're using the word size, 2 to the 32. There's no way we can design a function that will take this many inputs, map them to this many outputs, and not do collisions. But instead, what do we want? What makes a good hash function? Is, say my hash function is 0 for all the keys. Is that a good hash function?
It's an excellent hash function.
What's wrong with it?
You would put everything in one, so then searching for it would take a long time.
Yep, searching takes a long time. We don't do sorting with this. Yeah, searching takes a long time. String submatching will take a long time. It's horrible.
So you want one that distributes stuff like evenly over all that.
All right, so we want something that looks sort of random. The ideal hash function takes an input and gives it a random output, and then stays consistent. So when it sees an input, returns the same output. So I think distribute is the keyword here. What's wrong with this hash function? If it takes random data, it's going to distribute it randomly. That's true, so that's all good. But what data that we might see in real life will make it behave badly?
K is the series of characters, right?
Maybe.
It just could be anything. But we know for sure that L will be larger than W.
Say L is 1,000,000.
Okay. Well, that sucks.
Oh no, that in itself, that doesn't suck. That's what lets us do substring matching really fast, even if we have large strings.
Same for 2 to the W though, because then it'll be much larger, like the number of.
Yeah, but that's okay. So I'm okay with doing this as long as all the values here are distributed sort of uniformly here. So that's fine.
Okay.
But I'm arguing that there are some values which will make this hash function behave badly, and that those values are so simple that we might see them in real life. Okay, what if all these numbers are, what if all the digits are even? So B0 mod 2. What happens to K?
Oh, you're saying that instead of 2 to the W, we're just using 2.
So no, the modulo is 2 to the W. Say it's 2 to the 32.
Uh-huh.
So D are the digits that make up my key. So what if the base is 2 to the 8? So I have digits from 0 to 255, 256 of them. And all the digits are 0 modulo 2. For my substring matching example, what if all the characters in the substring are even?
But it's not.
Or get hash the same thing.
Not the same thing, but there's a problem. They will hash to, so if all the digits are 0 modulo 2, then what about the key? Yep. So it's just like when you have numbers in base 10. 10 happens to be divisible by 2. So if your last digit is even, then the entire number is even. That makes sense, right? That's math. Please not. Tell me that I'm making sense. Okay. So here the base is 256. And it's also divisible by 2. So if your last digit is divisible by 2, then the whole number is divisible by 2. So then if I take this key modulo 2 to the 32, then the hash is also going to be divisible by 2.
Why does it
Yeah.
the hash
Okay.
is divisible by 2?
Um, so it matters because this is supposed to be my universe, right? These are supposed to be all the outputs. And I'm saying that if my inputs look like this, then the hash function will not distribute them uniformly. Instead, if this is my possible set of outputs, the hash function will always put outputs in this half. So the outputs will always be here. And these are the numbers that are divisible by 2. So these are even, and these are odd. And this area gets no love. Absolutely no number will hash here. So
Wait, what about something
With
that
all
ends in
odd
odd?
digits, yeah.
something with all odd digits.
Yeah, say you
'Cause
just-
you're
you have
asking-
all A's rather than all B's in your substring, or in your string.
Or
All
if just
odd
your
digits.
last digit was odd.
If all the other digits are odd, then your last digit is odd, and then you also get something odd, right?
Yeah,
Right,
so would half of
there's
them
a
go
pattern,
to?
but there's an even distribution.
Well, if your hash function is always odd, then it's not an even distribution. It's
Wait, our hash function? I thought we were talking about
Isn't it even
key.
if your key is even and it's odd if your key is odd?
yeah, so that's bad. Because if all your keys happen to be even, say if we're doing the nucleotides, and the nucleotides are A, C, G, T, if they happen to be encoded as, say, 0, 2, 4, 6, then these are all even. So the hash function will always be even, and I'm wasting the last bit. So if I'm building a hash table, half the entries will be wasted. They'll never get anything in there. I'm just wasting memory.
So if you could guarantee that your inputs would be evenly distributed, right?
So if your
Then
inputs
your-
are random, then a hash function, most hash functions will do a good job of producing a random output. The problem is real life inputs are not random. For example, if you get, aside from this, if you get data from a camera, so if you get your color pixels from a camera, then because of noise, those might have the last few digits, the last few bits always be the same thing. Also, it seems like in real life, Knopf in his book argues about this. It seems like in real life there are a lot of sequences that look like that, that would make your hash function behave poorly. So again, the keyword is distribute. If some non-random property in the input is reflected in the output, then that's a bad hash function.
Would you gain a lot of time from your mod operation? Because mod in mod 2 to the n, you just truncate any bits to the left of that.
Yep.
Most significant.
Yeah,
right?
so that's why we would do this, right? That's why we're even considering this case.
Because that'd be really nice to be
Yeah.
able to not subtract.
So modulo is faster, but in return my hash function is crappier. So usually we prefer, it turns out that in practice, nicer hash functions give better speed improvements overall. So if you think of how a hash is laid out in memory, you'll see that because of caching and everything, it's better to take more time on the mod function and use up all your memory for the hash table. So this is why we don't use this and we use this, not because of this argument. So good question required a lot of talking and remembering what's a good hash function, what's a bad hash function. Thank you. Okay, let's look at the code a little bit. Everyone looked at it, right? So this time we have modules. We don't have everything in one big file. Can someone tell me what are the modules we care about and why?
Well, probably the ones we have to code ourselves. So,
Okay, let's start with that.
subsequence hashes, interval subsequence hashes.
Okay, so these are all in DNA-seq, right?
Yeah.
So the module is, so yeah, the pset helpfully says that you need to update, you need to upload this file because it's the only file you need to modify. So everything that we need to write is here. Now, pretty much everything that's in that file needs to be modified, so I'm not going to list them out. What else do we want to read in that pset? Okay, where's rolling hash?
And DNS values.
So what's different between the API in rolling hash and the API that we talked about last time? Yes.
Rather than having the what we call it, pop, or skip, and something else, this one just has a slide, which does everything in one operation.
All right. So we had append and skip. And we built some beautiful code with that, and we looked at some fancy math because of it. But it turns out that for the pset, we can get away with slide. And we started from slide and built these two methods last time, so I'm not going to explain slide again. It's exactly what we had in the code before we started breaking them up. OK, so this is the rolling hash. It is good. Do we care about anything else?
I guess you can look at the rest of the code if you feel like.
You can look at the rest of the code if you feel like it. Yep. So I highlighted one file that might be useful, and that's kfasta.py because that file has a FASTA sequence class, and that reads from a file and returns something. And the important thing is it doesn't return a list. If you remember the docdists, docdist1 through docdist8.py, fun times, what we had there was we took the input file and we read it all in a list. This time we're not doing that. We're writing, 20 lines of code instead of what could be 5 lines of code to read the input. Why is that? Less memory. OK, so if we're doing it this way, chances are that if we tried to shove the whole input into memory, it wouldn't fit. And it would crash, and you'd get 0 on the tests because of that. So that's not good. So what do we use instead? Does anyone know what this thing is called? What this class is called? Iterator. Very good.
Faster.
I think the letters are bio acronym.
Oh, okay.
Does anyone do bio here? I've seen that before. So it's a bio thing. Let's not worry about it.
Okay. Well, you could use that for any type of file. Like, you don't have to use it just for bio files.
Well, presumably it takes advantage of the format that they're stored in and gives you a list instead of something else. So how does an iterator work? Suppose you're building your own iterator. What do you have to implement? OK, let's start with next. That's the fun one. What does next do?
It's like pop.
OK. So it's like pop. In what way?
Use the next character.
OK. OK. And what happens when you're at the end of the list?
It stops.
How do you stop?
Here's the exception.
OK. So next we'll either return an element, that's the next element in the sequence that you're iterating over, or it will raise a stop iteration exception error. Oh, just stop iteration. Cool. So what's the other method? Someone said it before. Say it again. Iter. What does this do in an iterator?
It returns itself.
All right, very good. In an iterator, this is how you will implement it all the time. Does anyone know what's the point of iter?
So you can return an iterator because that's what it told us to do in the pset.
Okay, so iter returns an iterator, but it doesn't. You don't have to start from an iterator. So you can start from any object, and if it has a method iter, then it should give you an iterator that iterates over that object. So if you have something like a list, 1, 2, 3, 4, then if you call iter on this, you'll get an iterator for it, hopefully, right? And this is what Python uses when you say for I in. So behind the scenes, whatever object you give it here gets an iter call, and then that produces an iterator, and then Python calls next until stop iteration happens. So you can write an iterator that almost behaves like a list. You can use it in these for each instructions, and it works as if it was a list, except it uses a lot less memory because it computes the elements. Hopefully, every time next is called, you're computing the next element that you're returning. If you're storing everything in a list and returning the elements that way, that's not a very smart iterator. Okay, let's look at the last page. So the last page has an iterator on top, and the iterator computes, given a list, it computes the reverse of that list. And you can see that it doesn't reverse the list and then keep the reversed list in memory. Instead, every time you call next, it does some magic with the indexes. I think the magic is called math, and then it returns something as far as long as it can. So this is how you implement reverse without producing a new list. If the original list was say had n elements, then if you'd produce a new list, you'd consume order and memory. This thing consumes order 1 memory, and the running time is the same, asymptotically. Okay, any question on iterators?
So it's going from the very end, to the very beginning, and then it's stepping back.
So reverse, if I give it the list 1, 2, 3, 4, I want reverse to give it back 4, 3, 2, 1.
Yeah.
Except it's not going to return a list, it's going to return something that I can use here. Okay, yes?
Is it ever possible to like sort of rewind the iterator to like sort of reset it?
Okay, is it?
No.
Nope. So Python iterators are simple. All you can do is go forward.
Okay.
The reason that is good is because you can use them for streams. So if you get data from a file, or if you can get data from the network, you can wrap it in an iterator. If you wanted to support resume on data that you get from the network, you'd have to buffer all the data.
So you would have to call the iter method again and work
Yep.
further.
Yeah, if you want to rewind, get another iterator. Okay, that's a good question. Thank you. So these are iterators. Now we're going to go over some Python magic, which is called generators. So look at the iterator code, and then look at the equivalent code right below it. So 12 lines of Python turned into 3 lines of Python that do exactly the same thing. So the reverse method will return an object that is an iterator and that you can use just like the iterator in the reverse class. Do people understand what that code does? If you do, I'm so out of here. We're done. What does yield do? All right, that's the hard question. What does yield do? We'll probably spend the rest of the recitation on the answer to that question. You're asking all the hard questions today, man. So yield. Does anyone know conceptually what yield does? Not in detail, just what's it supposed to do so that the rest of the code works? Yes?
If you're driving someplace and there's a yield sign, you pause.
Okay, Python yield. So I like the word pause in there. The word pause is useful. So say instead of implementing this, say we're implementing subsequence hashes.
Can I like spit something out that keeps going?
Yep. Okay, so suppose you're implementing subsequence hashes. What's the worst possible way you could implement this? Okay, so the worst way is to go all the way brute force, don't use rolling hashes, don't use anything. The next best way is to make a list, right? So you're going to start with an empty list. Then you're going to use the rolling hash in some way. And in some loop, you're going to say list.append e, and then you're going to return the list. Does this make sense? Okay, what's the problem with this code? Gonna have a huge list. So the way we fix it with iterators is we remove this, we replace this with yield e, and we remove this. And now it's a generator. And now this consumes a constant amount of memory instead of building a list. And as long as you only want an iterator out of this method, you'll get the right thing. Your code will still work in exactly the same way. Okay, so the big question is, what does this guy do, right? This is where the magic is. So I already said as a first hint that this guy will return an iterator. So can someone try to imagine their Python and see this? So suppose you're Python, you see this. What do?
You wait for some sort of command of some sort, right?
No, let's try something else.
Okay.
So the execution of this pauses. What happens? So we're looping somewhere. We got the yield. We stop. What's the first thing we do? And so you're saying you return e from this guy?
Figure out how E is being used.
So I want to return something. I want to return something else from this. So I want to use this as if it was a list. Yes?
Can we store E somewhere?
Okay, store e somewhere.
Do you return a pointer of E?
Almost. So there's a word for the object that I'm returning. So I want to use it as if it was a list. So I want to pretend that I had return list in this method, right? So what's the closest thing to a list that I can return?
An iterator.
An iterator. Thank you. All right. So we will grab some information from here. We'll put it in a nice box. And that box will behave like an iterator. Okay, so the first thing, someone said put e away, so that when we call next, we're going to spit that out. What else do I need to put away? Yep. So this is a lot of magic. This tiny box actually has a lot of magic in it. Because when I call next, I want to get e, but I want to come back here and keep going. Right? So I have my code that's using the iterator. And there's this code here that's sort of in a frozen state. Did you guys see any movies where people are frozen up and then in the future they're unfrozen and they start moving again? All right, cool. So this is like that. This takes up the whole function, freezes it up, and puts it in a box here. And it returns an iterator that can use the box in the future. So when you call next, it gives e, which is the guy that you put in here, and then it takes the function out of the box, unfreezes it, and lets it run again until it hits yield again. Then what happens the next time it hits yield? So you're looping and you're yielding again, and say this time you're yielding.
Just do the same thing.
Do you put it in that iterator or do you make another iterator?
Same iterator. So while this is looping, the code outside should get the values that it's yielding. Right? So this has to behave as one iterator. So the code is unfrozen. It's allowed to execute until it says yield again. And then it says yield with a new element. I put this guy in the box. Then I return the old guy as the return value for next. And then it's frozen again. So this guy is still in a frozen state. In the movies, I think you're only unfrozen once, and then you keep going, right? And there's a happy ending. Where here, every time you call yield, you're frozen again until someone calls next. Does this make sense?
It's kind of like Groundhog Day then.
Yes, except you're allowed to go forward. So
So no, but
This-
it's like
this
it's
keeps
just
going
unlocking
forward.
Up, though. So it's looping. It's the same day really. It's doing different things though.
yeah, but all your state is saved. So there, some of the state is rolled back.
Okay.
Here, all the state is saved.
Okay.
Okay, but if that analogy helps, keep it.
When you call next, are you computing E or E prime to be returned?
So when you're calling next, you're computing E prime and returning E.
So the value you get from next is pre-computed.
So the value you get from next is what you yielded before.
Wait, so you would just take subsequence hashes, make an instance of that, and then just by putting in yield, now it's magically become an iterator, and you can call .next on it.
Yep. And inside, you don't have to know that it's an iterator. So you don't have a method next here, right? I don't implement next or iter here. I write this as if it's printing stuff to the output. Right? You can think of yield as a print. If you wanted an iterator, then pretend you're printing what you want to iterate over, and instead of saying print, you say yield, and then you use that. Okay, now what happens when we're done? What happens when this loop is done and you return from this method? We said there's no return value.
It raises stop.
So when we return, it's going to keep in to remember that it's done, right? And the first time it has some element here that it has to return. Right? So every time you call yield, we put a new element in the box and we return the old one. So now we would return the old one. We would return E prime, take it out, and put done in the box. So in the future, if next is called again, raise stop iteration. No more freezing, unfreezing, because we're done. We returned.
So if you called next, it would just give you nothing.
It has to raise this exception.
Yeah. So I mean like, I see. It would give you red text then.
If you called it directly, yes, it would give you red text.
Okay.
Yes.
So this takes a sequence or a list, not another iterator. Is that right?
This, what's
Sorry,
this?
the
pseudocode here?
Yeah, this.
Not necessarily.
Or you could give it a procedure.
I can give it an iterator if I'm iterating over it using for in.
Like for something in an iterator, yield that something, and then it's like,
Okay.
Yeah, that's a good point. I'll get to that later when we talk about how we're going to solve the p-set. No, we're not solving the p-set for you. But we'll talk about it a little bit. But yeah, that's a good point. So there's no reason why you can't have an argument here that either a list or an iterator, and then you're iterating over it. And then you have nested generators. So you have generators returned in other generators, and you have a whole chain of things happening when you say next.
Wait, so this is a generator then because it produces it is an iterator though.
So a generator returns an iterator from this method. So a generator acts like an iterator, except when you call next, it unfreezes this code here, and it lets it run.
But I mean, it's basically an iterator then.
Yeah.
But we're just calling it a generator because.
Because
it's
there's a
not-
lot more magic.
Okay.
So an iterator just says next and iter. This is all that an iterator is, nothing more. Any object that has these two methods is an iterator.
Okay.
Now a generator is a piece of Python magic that lets you write shorter iterators. So 3 lines as opposed to 13 lines. And we came up with a way to turn in a code that would build a list and easily turn it into a code that uses a generator and that uses constant memory instead of building that list. Exactly. Okay, the generators make sense now? Yes.
you wanted to loop through all of the values in the generator, do you just have to wait until the exception's raised, or should you like keep track of how many things are going to be in that generator?
So when you have a generator, you have no idea how many things there are. That's a good point. So you're wondering if I have an iterator, say any iterator, not necessarily a generator, how do I know how many things it's going to return, right? Do I have len? I do not have len. So an iterator does not have len. So you have to iterate through it. And most importantly, some iterators can never return. So you can have an iterator that streams data for you across the network. Or you can have an iterator that iterates over the Fibonacci numbers. That's an infinite sequence, right? It's never going to end. So len would not even be defined then. Good question. I like it.
Is there an isNext method for either iterators or generators?
Nope. This is what you get if there is no
Okay,
next.
so basically, if that is returned, then
Yeah. So in Java, you have this belief that you shouldn't get exceptions. You should be able to check for them, right? So maybe that's what you're asking. So if people coming from Java know that anytime a method raises an exception, there should be another method that tells you whether this first method is going to raise an exception or not. In Python, the exception is just raised. So exceptions are not a lot more expensive than regular instructions because we're using an interpreted language and it's already reasonably slow. So you can do exceptions for free. Yay! So this is how it works. This is how for in works. Every time you do a for in, an exception is raised.
we don't have to catch that then.
Nope. The for in catches it for you.
It's tricky stuff.
But it's nice because then you can build any iterator that acts like a list, and then you can do even more fancy stuff and build a generator. And you're using constant memory instead of order and memory for producing an order and size list. Yes?
So if we did pass in an iterator and then just yielded what we passed in, yielded the iterator, would that just essentially delay everything by one?
So you're yielding the iterators next, right? You want to yield the iterators next, because if you yield the iterator object, you're going to return that object every time. Right? So you're thinking of something that
So you need to create.
yield e dot next, right?
Right.
You can have a method that says this is the method, and then you take in an iterator, and then you yield e dot next. But then you'll basically get the same thing.
It's the same thing. But
Yeah.
is it delayed by one or no?
Nope. No, so you have to work through this to convince yourself that it's not delayed, because so if it would be delayed by one, what's the first thing that you're yielding? Yeah, so no delaying.
Okay.
Okay. Cool. So let's see. What do we have to implement in DNA-seq? Subsequence hashes. Do people have an idea of how to implement that now? Yes? Does it make sense for everyone? So you build it as if you were building a list, and then you use yield to make it fast. And by fast, I mean less memory. Okay, how about interval subsequence hashes? The one below.
Is that just like rolling a hash, but except you like have like a step in your range?
Okay, so it's like having a step in your range. So how can you do that? What's one way of doing it?
For your hashes.
Did anyone solve the p-set yet? Yes, okay, how did you guys do it? Wait, no, that's a bad question because you guys can answer too much. So interval subsequence hashes versus subsequence hashes. Did you copy paste the code?
Absolutely.
Okay, so one way of doing it is copy pasting the code. The problem if you copy paste the code is then you're not dry. There's this engineering thing. Dry means do not repeat yourself. So if you're not dry, if you copy paste, then suppose you find the bug later. Suppose you run the big test and it crashes somewhere and you fix a bug in subsequence hashes.
Oh, we're supposed to like call subsequence hashes from interval subsequence hashes, right?
That's another way of doing it that is dry. So this way you're not copy pasting the code.
We're inlining code. It's actually better than.
You're inlining it manually, right? Optimizing. All right. So the problem, if you do this on a large scale, like when you go work somewhere, is that you end up with 20 copies of the same code, and then 5 of them have bug fixes, and the other 15 don't, because people forgot where they are. So ideally, try to keep your code dry. It won't matter for this